SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We have discussed the traditional methods of mineral inventory estimation, including the one which is the inverse distance weighting method. So, from for a few of our discussions, for the few of the coming lectures, we shall be discussing just getting ourselves introduced to the method of the geostatistical ore reserve estimation, or the geostatistical method which is employed in the in mineral inventory estimation. So, essentially, before getting into the geostatistical method, let us first try to know what kind of variable we are actually dealing with. By this time, we got a very fair idea that the kind of parameters which we are trying to understand in relation to the ore deposit, evaluation of the ore body in terms of its quality and quantity, are the attribute values, are the variables in space. So, certainly we are talking about variables and the variable in space. So, whenever we are talking about, suppose I could just draw a very simplified this cuboid, let us say it represents an ore body. So, it has got a dimension of length, breadth and height, and this represents an ore body. So, it has got its dimension, extends in 3 dimension x, y and z, and we are talking about the parameter which is the grade of the ore body. And we have already got some idea that this grade that we are talking about in an ore body is not the one which is going to be of a uniform value, same value all throughout its dimension in length, breadth and weight. Rather, it is a rule rather than exception that the grade is not actually same everywhere. There are domains in which the grade might decrease in one direction, or the grade might vary more in one direction and less in other direction. Suppose this is the strike of the ore body. If this is the strike of the ore body, and this is the width of the ore body, and this is the depth of the ore body. So, what basically might happen, that the variation of the grade might be different along strike or across strike or along depth, which is very usual, because it is a result of a very complicated ore forming process, which has resulted in bearing very few exceptions, like a banded iron formation, where an unenriched, unaltered primary banded iron ore can possibly have a very uniform content of iron in a infinite in the strike direction. But in most of the types of deposits, the hydrothermal sulphide deposits that we generally try to do this exercise, they will always have such kind of variation. So, they vary in space. So, they are variables in space. And so now the other point that we could possibly remember about this is that the grade which is calculated, suppose the grade calculated any point in space over here, and the grade which is calculated at a point which is infinitesimally or is a very close in space to it, or a grade which is calculated at a point which is far off from the point that we are referring to it at this point here. What we see is that they will generally not be just be very different from each other. In one of our procedures of the estimation through conventional method, which is used for the IDW, the inverse distance weighting method, where we were discussing about having a block which is defined here, and we wanted to compute the grade at the center of this particular block with certain points where the grades are known, and these points were denoted as G1, G2, G3, G4 and so on, and they were at distance of D1, D2, D3 and D4 likewise, and we saw a calculation procedure in which if we are trying to find out a weight as Wi for finding out the grade here by using a simple formula of Wi Gi, and this W being varying from 0 to 1 and sigma Wi is equal to 1, and in this we discussed that the value at any point in space will be influenced by its nearby neighborhood points, and shorter is the distance, greater is the influence. So, we would expect that this Wi's will have a higher value for points which are closely spaced compared to the points which are far away. And in that we also raise the question that what is the kind of the spatial limit that we can use this IDW. Now, if we try to understand this geostatistical method, that possibly would give some give an answer to this question that we raised before. So, before we get into all this discussion, let us be reminded of one very basic premise, that whenever we are talking about variables in nature, so they generally could be between two extremes. They either they are random or they are deterministic. In case of random, the observation, any two successive observations either in time very closely spaced or succession in space which is very infinitesimally closely spaced, or even any space interval. So, no two successive observations are dependent on each other. So, they are just independent of each other and treat them as random variables. So, the value of a particular variable that is occurring at a point here and a point which is away from it in space will be absolutely independent of each other, and we call them as behaving as completely as random. The other one is that in the deterministic case, every successive value will have a very well defined relationship with the previous one, like say talk about where a body is moving with a certain force applied, its velocity with time, it follows a very well defined deterministic relationship. Now, can we think of a situation where a variable will behave exactly something intermediate between the truly random or truly deterministic, that we will call as regionalized variable. As regionalized variable. So, this regionalized variable means that if we are this is a representation of something in space, and each nodes are our point of observation. This has been drawn in both the directions x and y, and also we can think of the diagonal directions as well. Suppose we are talking about an observation which is made here at any point here, then the value which are or the value of the variable. So, here in the, as far as the spatial data are concerned, we are talking about. So, these are variable in space, and we are calling them as spatial data. So, the spatial data means if we are defining a coordinate, if I am representing this as 0 and 10 and 10. So, this is a grid where it is 10 cross 10 100 points, and each one's coordinate is known, and that is the data in space. So, we can think in terms of any of the attribute its value to be determined here at these points, and that is the attribute data, and we are talking about the variation of that attribute data, and let us that attribute be the grade, and this let us say that this variable is our grade. We are assigned with the to understand how the grade is varying in a particular taking only the 2 dimension as the example. Even we can first start with this with a 1 dimensional case. So, here what basically had it been a random variable, then it would have been totally independent. Any of the values which are spatially close would have been independent of the value that is measured here, and the behavior of that variable would have been easily depicted by using some kind of distribution following a normal distribution or any kind of a statistical distribution, where taking the very simple example of a normal statistical distribution, where we represent the characteristics of a normal distribution by its mean, which is mu, and the variance is sigma square, and we know what are the formula for calculation. For example, when we are talking about mean, we know that this will be sigma x sigma xi divided by n. So, this gives us the mean, and when we talk about sigma square, we talk about a situation where it is sigma. So, this will be mu minus x square divided by n minus 1 kind of formula, which this is for the variance and this is for the mean, and here this gives us a central tendency of the data in terms of its dispersion, and it is expressed as sigma square, which is the variance. So, this particular variable, which is our regionalized variable, is expected to behave in a way which is intermediate between random, truly random and truly deterministic. Then we see exactly what it does. So, what happens is that the value this value which is the most closely spaced influences the value or has some relationship or the strongest relationship with the value here, and that relation actually dies out as we move away from the point. So, this relationship is quantified in terms of a quantity which is like variance, which is actually a semi variance which is given by a formula. I will first write out the formula. The semi variance is represented as a quantity as gamma h, and that is actually 1 by 2 n sigma I equals to 1 to n h. If I say I am using the regionalized variable and my attribute is grade, let me represent it as value as g, let us say. So, I would say that g I minus g I plus h squared. So, this is a quantity, this is a thing gamma h, which is the semi variance, which can be estimated in this way, which one can see the relationship which looks kind of a little bit not that very far off here also. So, the connotations here is gi. Let us say for example, this is the point I and this is the point which is I plus h, and in this grid that is shown here, let us say that each separation of the grid be represented by h, and this representation of this h. So, that means it can be thought of in terms of multiples of h. For example, this point is away from this point by a distance h, and this point is away by a distance 2 h, this point is 3 h. For example, if I take the distance here, so this distance is a distance h, this distance is 2 h, this distance is 3 h, and so on. So, here this h is basically called as the lag, and then what exactly happens here is that if there are 10 points, suppose consider any particular one line on which there are 10 data. So, these 10 data are separated each by a distance of h. So, if I have to calculate this kind of formula of taking the value at any point of determination with respect to a value that is determines just h distance away, then I will get n minus 1 number of pairs, 1, 2, 3. So, like that I will be getting, if there are 10 points and 10 points with 1 h separation, I will be getting 9 pairs of such points for which I can calculate this value by taking g I minus g I plus h squared divided by this 2 n, which is exactly the value as the total number of points as n minus h, and it will be summation will be over I is equal to 1 to n h, means when the lag is 1 there will be 9 points, when the lag is 2 there will be 8 points, the lag is 3 there will be 7 points, and so on. Now, what happens is that if I am plotting, if I do have to plot h versus gamma h, this is why the conventionally plot is done. As it will be understood from this formula that any particular point on which we are doing the measurement, if we done on this very same point, then we will get a value of 0, and as h will increase to h, 2 h, 3 h and 4 h and so on, this value is likely to increase. So, this is the general behavior of a regionalized variable. What exactly what type of regionalized variable we will discuss now, where this value of gamma h starts from a value of 0 at the origin and then goes on increasing and attains a certain value, after which it becomes flat or parallel to the x axis, at which point it is called the sill, and the value corresponding to the sill is actually the sigma 0 square, which should be same as the. So, that means the value, the variable is behaving like a random variable after a certain intervals. So, that particular interval exactly at which the value has become parallel is something which can be represented as a. So, here it is the sill where the variable has become the parameter of interest. When it is calculated, the semivariance has actually taken a value, constant value had become flat, that is sill, and this a will be called as the range of this semivariance, and this will be called as a variogram or a semi-variogram. It will be maybe different books will with differently terminologies. So, let us call it as a semi-variogram. So, this is essentially is an idealized semi-variogram. Now, let us so this is a very basic idea about the behavior of a regionalized variable, which behave something intermediate between truly random and truly deterministic, and the value the value of the variable is has a strong dependence on values which are measured at very closely spaced or infinitesimal small intervals. Now, there are two other things which can be talked about this regionalized variable is that what is we are considering the regionalized variable in convert with respect to this particular space, and we have put it on a 2 dimension. A third dimension can always be there, and we talk about a variable, let us say, which is our grade. Now, this regionalized variable is always referred to in connection with something which is called as support. Examples of regionalized variables are many there. Even a surface elevation that is measured at different points on the earth's surface can be a regionalized variable. Depth of water table can be a regionalized variable, and there are many such examples. So, when we talk about a regionalized variable's behavior in different directions, in x, y and z directions, in depending on the volume of that, because when we are talking about an ore body which is very finite, it sits in its dimensions measuring in whatever, say even a kilometer long or several tens of meters wide, or even going to 700-800 meter deep. So, when we say that this variation will be different in different kind of directions, so what we basically mean by is that is the support of this regionalized variable, that and each type of regionalized variable will have a different support. For example, the surface elevation on the elevation on the earth's surface can be thought of varying only in terms of kilometers, whereas an ore body grade can be thought of can be visualized as varying within just tens of centimeters or tens of meters, and that also might vary in different directions like along strike, across strike and so on. And then what is the other aspect of the regionalized variable is that a regionalized variable, the way we are visualizing it, it could be either stationary or it could be a non-stationary. For example, in this case, within this space, let us try to explain, or let us try to understand what we mean by that. So, there are many of these points on which the regionalized variable of interest, let us say grade, is estimated, and let us say that we are calculating, kind of taking these 9 points, we calculate an average and assign that average to the central point, and then let us move this window in any direction which we want, left or right or top or bottom, and go on calculating the average of that value for each such central point with respect to these 9 neighboring points. It might, so the first case where the regionalized variable is stationary, we will find that the mean computed at different points all within this spatial domain, or it might be just a small representation of that, that this mean will maintain a uniform value or the same value. So, it is a situation where the mean is not changing. The other case, suppose a mean is computed over here and a mean is computed over here, and the mean is computed in all other successive nodes here, they are going to be different from each other. So, either the computed mean on this either will go on increasing or decreasing, either of these two things might happen. So, if we look at the actual formula for calculation of the semivariance, then it would look something like this. I am just representing just as n, and this will be sigma. Let us represent our variable as x for the time being. So, it is x I minus x I plus h minus divided by n. Now, this expression is something which is to be looked at. Now, the second part of it is actually representing the mean, because this is x I minus x I plus h computed over this n is nothing but the mean of it. So, if it happens to be a non-stationary regionalized variable, then this value is not going to be same as same, and it will not, because this will have a significant value if the value is non-stationary. If the value is stationary, where the mean that is computed at each point is same, then this will reduce to 0, and this formula will reduce to the earlier formula which we derived, or we just stated that this is because this term, this particular term will vanish for stationary regionalized variable, whereas this term will be significant if the situation is it is a non-stationary regionalized variable. So, the non-stationary regionalized variable is actually characterized by something which is called as the drift. That means, the as we have seen here with respect to this particular diagram, that the regionalized variable, if non-stationary, it will have drift, means the mean values which are computed at successive points are going to be either in an increasing order or a decreasing order, and that will be that is actually designated as the drift in the regionalized variable. So, whereas the non-stationary is quite more usual for variables to be non-stationary rather than stationary, but the catch is that we can always construct something which is our experimental semi-variogram or the calculated semi-variogram, which can be done only if the variable is stationary, because it will have a range which is the designated by the A that we did in our previous graph, and it will behave in certain manner. We have only shown it by an idealized diagram, which was which we call this particular diagram, where we discussed that it is an idealized semi-variogram. So, it essentially is a spherical shape, because it almost up to this point it can be thought of as a radius of a circle, and similarly. So, these semi-variograms of many different types of regionalized variables can be thought of being approximated by such kind of models. Such for example, the model could be spherical. We will discuss about this point a little later, about the stationary and non-stationary and how to deal with them. May not be up to that much of a detailed or not that much of rigorous exercise, but just for our general understanding at this level. So, a semi-variogram would be spherical, where it could be represented as gamma h will be equal to sigma 0 square. Okay, I will just write it here. Spherical is gamma h is equal to sigma 0 square. Sigma 0 is the seal, 3h by 2a minus h q by 2a q. So, where h is our lag and a is the neighborhood, that means the range. It also a is also called the range or the neighborhood within which the relationship is valid. So, exactly what we are trying to understand here is that the regionalized variable characteristic, that they have a spatial restrictions or the spatial dependence, that is actually quantified by the parameter which is a, that is the neighborhood or the range. So, that means we can expect our variable to be behaving like a regionalized variable with the any particular point, the measurement to be influenced by its nearby point or the neighborhood points within the spatial limit of this range or the neighborhood. So, the spherical model. So, this we are not getting into the derivation, or we are also not just getting into any other exercise on that. A semi-variogram could also be an exponential semi-variogram, where gamma h could be sigma 0 square into 1 minus e to the power minus 3 h by a is also in relationship to this h and a, or we could also think of a very simple type of semi-variogram where gamma h will be simply alpha h. That means, it is just a linear situation like this. If it is h, this is gamma h, it would be something like this, where for the part within the part which is our a here, for this part we can always think of that is behaving very much like a straight line, where gamma h could be computed given the value of h at any point within that particular special restriction. So, this is a beginning, the very introductory step towards making a very beginning or the very preliminary understanding on the principle, I would not say theory, the principle based on which this geostatistical O reserve estimation is based, and we will continue discussing on this. Thank you.